Today's presentation, Wide Area Blackout Prevention Using Advanced Models. This has been my passion for about 30 years now. I used to work in an operations control center back in the 1970s, and modeling the system has always been something that I've really enjoyed doing. I've been in the industry for more than 50 years. I'm a life senior member of IEEE, and I hope this is a lot of fun for everyone who attends. So if I think about today's power grid, the models have to be enhanced, and the best way to enhance them is to examine past incidents and review the types of loads we have out there, and then introduce recovery models to the users. And then finally, we're going to discuss how Prescient utilizes the enhanced models. When I think of the energy grid, I think the energy grid is a lot like the belt transfer machines we had back in the late 1800s, where we put a water wheel near a river someplace and spun a wheel. And so I'm thinking of that, and transmission lines are like they're the drive shaft that we had in the belt drive systems. And we model them very accurately. We calculate the impedance of the line by taking every pole into account and every conduit into account for underground lines. And energy sources, they're modeled with high accuracy. And transformers, which I equate to pulleys, they're modeled with good accuracy. I say good accuracy because all transformers have several taps, and we model them at one of the tap positions. And distribution lines, which are the power takeoffs, we model them with some accuracy. We don't spend the time to calculate the impedance of a distribution line like we do a transmission line. And then we get to loads. So loads are modeled for steady state conditions, and we make the assumptions that motors ride through fault conditions. And this is the weak point in the models that we're using. If I look at past incidents that happened, the August 14th, 2003 Northeast blackout, that was caused when multiple transmission lines sagged down into things under the line. And when that happened, there was a huge change in VAR loading on the transmission system. A more relevant example is the September 18th, 2011 Southwest blackout, where we lost voltage control. And that loss of voltage control occurred when a 500 kV air brake switch was operated out of sequence. And then April 7th of 2015, we had a Washington, D.C. area low voltage disturbance. And the reason why that didn't go to a blackout was the time of year. If that same condition happened in July or August, we would have had another great blackout. So during peak load conditions, a three-phase fault on a transmission facility can result in a multi-state blackout. And as electrification increases, the risk is going to increase, and it's probably going to include non-peak load conditions. So I'm looking at the type of loads we have out there. We have space heaters and process heaters, and we model them as constant resistance loads. Induction motors are variable power loads, but we really model them as constant power loads. You got to remember, when you're looking at motors, a motor speed is a function of motor voltage and mechanical load. So if the voltage drops, the point on the speed torque curve that intersects with the load torque curve changes, and the load produced by the motor is reduced. So fan and pump motors, they slow down when voltage dips occur. The concern we have is that air conditioner compressor motors can stall when voltage dips occur. And the difference is that the torque changes with speed when I'm looking at a fan and a pump motor, but an air conditioner is that's a positive displacement type pump. And when the speed changes, the load and the torque do not change. So anyhow, what we did is we put together a time voltage profile that shows a power grid with a fault on it near bus A. And I showed the voltage at 3 different locations when this fault occurred. And the scale goes from 1 hour to 20 seconds across the bottom. and the percent voltage is the vertical axis. And I'm showing a fault close to bus A. Bus B is impacted by the fault at bus A, and bus C is impacted by the fault at bus A. And what I'm trying to show here is in the red box, if the voltage drops to less than 25% for 32 milliseconds, I'm expecting that motors are going to shut down. If voltage drops to less than 70% for 75 milliseconds, that's the yellow box, and air conditioners, motors are going to stall, fans are going to slow down, pumps are going to slow down, but you get simultaneous motor reacceleration after the fault is cleared. If all the motors reaccelerate in about 10 seconds, you're home free. If the motors don't reaccelerate, you're going to probably advance to a wide area blackout. And the curves here are set up a little bit strange because I'm showing that I go from 100% voltage. When the fault occurs in 0 milliseconds, the voltage collapses on bus A. The 80 milliseconds time here, this is when the circuit breakers open that are feeding the fault. So you can see the stall time for an air conditioner is typically less than the clearing time for faults. And then between 80 milliseconds and 100 milliseconds, I'm getting some rapid voltage recovery. And then I get a slow voltage recovery after that up to 20 seconds. So what we did is we took different devices and we tested them to see how they're impacted by voltage. And we took a space heater, put it's 1,000 watt equivalent space heater. All the numbers that we're using here on these charts are unitized. So everything is unitized to 1,000 volt amps. And we tested space heaters. We had 1,000 watts at 100% voltage. We took the voltage to 70% and they drew 500 watts. That's what we expected to see. Then we tested battery chargers. On battery chargers, we were getting 1,000 volt amps at 100% voltage and a 70% power factor. We dropped the voltage to 70% and we still got 1,000 volt amps being consumed by the battery charger, but the power factor improved. It went up to 96%. So then we said, well, let's test the induction motors. So we tested a fan motor, and we had 1,000 volt amps, the equivalent at 100% voltage with an 80% power factor. We dropped the voltage to 70%, and the induction motor was drawing 500 volt amps, but the power factor dropped to 65%. Because what happens with motors, I have two curves I look at. One is the speed torque curve. Another curve I look at is the excitation energy versus speed curve. Once you drop below 80% speed, the excitation energy in an induction motor jumps up a lot. So we took pumps. We did some tests with pumps. We had 1,000 volt amps at 100% voltage and 80% power factor. When we dropped the voltage to 70%, we got 520 volt amps and 70% power factor. And then we did some air conditioning tests. So for the air conditioners, these are window shaker air conditioners, the 120 volt air conditioners you put in your windows. And 1,000 volt amps, 100% voltage, we got 95% power factor on those. And if the voltage dropped to 70%, they were drawing 100 or 1,200 volt amps at 95% power factor. So at a lower voltage, the power draw went up. But then we said, okay, what happens if I stall the motor and then try to reaccelerate it immediately? So I'm looking at an air conditioner motor, reaccelerating it at 70% voltage. We were drawing 2,500 volt amps at a 70% power factor. And so this is the type of condition we're looking at when you're trying to reaccelerate stalled air conditioners. And the air conditioner stalled because there was a fault on the system, and the fault was on the system for more than 80 milliseconds. Then, since we had our test equipment out, we figured we would test other things too. And we took a laptop with a discharge battery, and we found out that they would draw 1,000 volt amps at 100% voltage with a 60% power factor. if the voltage dropped to 70%, they'd still draw 1,000 volt amps with a 75% power factor. Then we repeated the laptop test with a charged battery, and we had the equivalent of 1,000 volt amps at 100% voltage with a 35% power factor, and we got the same results at 70% voltage. So this was testing we did in our lab to see how different things respond and to see if our knowledge of loads was actually reproducible in a test lab. So looking at this, we said, okay, what does all this mean? Well, when utilities evaluate loads on the system, they do it on a feeder basis. So if I took a 12 kV feeder and I was at 100% voltage, and I said the peak load was 400 amps, and this is the summer peak. Now the question is, how do all these loads get distributed? Well, what we did is we compared the April loading to the August loading. And what we found was that the April loading is about 50% of the August loading. And we made the assumption that the difference between the two loads is air conditioning. So we said the air conditioning load would be 50%, pump load would be 10%, fan load would be 10%, lights and heaters and things like that would be 10%. And so we broke this out and we said, this is what we think the load is going to be on a 12 kV distribution feeder with 100% voltage and 400 amps of peak load. Now, the circuit itself is probably a 600 amp circuit, but you don't load it up to its peak capability because you're leaving margin for load transfers and things like that. So anyhow, we took the values that I had in the preceding tables and unitized those and put them in here. And we said that, well, the total load on a circuit is about 8,300 kVA. And so that was 864 kilowatts of resistive load. The fans were 691 plus 518 kVAR. The air conditioners were 4,000 kW plus 1,300 kVAR. The total for the circuit was 7,400 kW, 3,600 kVAR, and about 8,300 kVA. This is at 100% voltage. If I take the same circuit and the voltage drops to 70%, at 70%, the kilowatts go down, the kilovars go down, the kVA goes down, and so I got a value like this. And then I'm saying, well, I'm really concerned about fault-induced delayed voltage recovery, and I'm looking at reacceleration. So if I'm looking at reacceleration, now I've got 70% voltage, and I'm looking at air conditioner reacceleration. And the air conditioner kW went up, the kVAR went up a lot, the kVA went up a lot. So instead of having a circuit with 8,000 kVA on it, I have a circuit with 13,000 kVA. So this is our analysis for one circuit. And so the concern we have is like, what are the precursors to a wide area blackout? Well, the voltage is going to be maintained near normal all the time. Under FIDVR conditions, fault-induced delayed voltage recovery conditions, the voltage sags, but you can't count on the load tap changer controllers on the transformers to actuate. They've got delays on them, so they're not going to respond in 10 seconds. And we also considered, well, what happens if overloads operate and trip the motors off? Well, it turns out that when you're at 70% voltage, the current is less, and with less current, the overloads are slower. So the concern is you want motors to reaccelerate within 10 seconds as the voltage is recovering. If they don't if they're not up to speed in 10 seconds, a system collapse is likely. And the concern we have is fault-induced delayed voltage recovery. It's a concern where you have a large amount of air conditioners. And this was initially identified as a concern in Southern California in the 1990s. I think it's going to be a problem across the whole United States as the temperature increases and as everyone's getting air conditioning in their houses. I live in Oregon. In 1980, it was unusual for every house to have air conditioning. In 2024, every new house is being built with an air conditioner. So the concern isn't one feeder. The concern is what happens if you have a fault on the transmission system and it affects many feeders. So we looked at what happens is the kilowatts went up by 130%, the kVAR went up by 250%, and the kVA went up by 160% when I compared the normal loading on a circuit to the fault recovery load on a circuit. If I have 4 feeders in a neighborhood substation that's rural, the load could increase from 3,300 kVA to 5,300 kVA. 20,000 kVA change in load, that's not going to cause a wide area blackout. That's not significant. When I look at city areas like New York City and a metropolitan neighborhood substation, typical feeders in New York City or substations in New York City have 20 feeders, and the load could increase from 166,000 kVA to 265,000 kVA. That represents the 160% increase in the peak kVA during reacceleration. If I look at a transmission line fault, this becomes difficult to analyze because how many substations are going to get affected by a transmission line fault? If I have 100 feeders in several neighborhood substations affected, the load increase could be from 830,000 kVA to 1.3 million kVA. So that's equivalent to a large generator. So we did these testing, and one of the concerns we have is that the tests we did were for one motor at a time, one load at a time. What we did is we used auxiliary heaters to drop the voltage to 70% on the motor we were testing. And we think you have to do stage fault tests to actually determine the impact. And we should be doing stage fault tests routinely. We should do them at neighborhood substations. If you do a stage fault test at a neighborhood substation, that'll validate the analysis that we've done, the load tests we've done. The issue always becomes, how many different loads do you want to test? Do you want to test 20 different air conditioners and 20 different fans and 20 different pumps? And when you start thinking about things like that, you say, well, maybe it makes more sense to do stage fault testing. And if you're going to do stage fault testing, we're thinking you want to do them when you're above 85 degrees Fahrenheit. So that says to me, I'm not going to do a stage fault test in April. I'm actually going to do my stage fault tests in July or August. And so I look at that and you say, like, well, historically, stage fault tests were a big risk, right? And the answer is that no, they don't have to be a risk now. If you put in a circuit breaker that's dedicated for stage fault testing and it's a trip-free breaker, the fault duration should only be 50 milliseconds. You're going to put the stage fault tests on one of the feeders leaving a neighborhood substation. So if you say, well, what happens if the stage fault breaker fails to open? Well, if the stage fault breaker fails to open, the substation breaker would open, and then you'd trip all the customers on that feeder. If you do a transmission substation fault, that would validate our network analysis. One of the concerns we have with putting faults on a transmission substation is we'd like to do it at a substation under 100 kV. So we're thinking you would do a test like that at 69 kV. And I mentioned before that we want to do these faults at 85 degrees air temperature, because it turns out that the air conditioner reacceleration is a function of the ambient conditions. If we got an air conditioner specialist involved, they could probably tell us the optimum temperature, the minimum temperature we had to do it at. But it has to be a high enough temperature to represent the the conditions that we'd be looking at during if an actual fault occurred. So thinking about stage fault tests, we think you could set up a stage fault setup in a neighborhood substation in 2 days, and 1 day to take it, 1 day to test it, and 1 day to take it down. And it cost about $150,000. The method is the reason why it would be set up in 2 days is it would be a trailer mounted circuit breaker, and the trailer mounted circuit breaker would be tested at the factory before it shipped. And so you do some acceptance tests at the substation, but the bulk of the testing on the circuit breaker would be done at the factory. A transmission substation fault, we're thinking 69 kV so that we don't have to get NERC involved. And that would probably take a 5-day setup with 1 day testing, 1 day takedown, and probably $250,000. So stage fault tests, in our mind, aren't that expensive when you look at the results of what you're going to get. The thing that's driving us that we're thinking about here is how do you transfer load across a system? And if you take all the transfer equations, the megawatt transfer, that's a function of the source voltage times the load voltage divided by the transfer impedance times the sine of some angle. That angle is typically going to be less than 10 degrees. But the thing of it is, under normal conditions, source voltage is 100%, load voltage is 100%, and I get maximum power transfer capability. If the load voltage drops to 70%, I can only transfer about 70% of the power. The equations for megawatt transfer and megavar transfer are different. The MVAR transfers are a function of the square of the voltages. So I can transfer a lot of VARs, or I could transfer a lot of watts, but I can't transfer this. I don't have the same relationship in both equations. And you got to remember the transfer impedance includes all elements. So it would include the source, the impedance of the power grid, plus the impedance of the load. So when I'm looking at fault-induced delayed voltage recovery conditions, the load voltage would be 70 to 80%. The transformer impedance would be reduced because what I'm doing is I'm changing the impedance of the load. As I'm reaccelerating the motors, the impedance of the motors are different, and the angle is going to increase. But it's still the same equations, and these equations are somewhat simple to look at. But when I look at a really complex network, we always have questions. How good is our modeling? And a stage fault test would prove that the modeling is accurate, and that's the thing to do. So we think you have to transition to enhanced models. We recognize that the load varies with voltage. We did tests on individual loads to verify our analysis was correct. Renewable energy sources, they vary with environmental conditions. So that means that in addition to changes in load, you have to look at changes in energy sources. And this is a known concern. FIDVR has been around since the 90s. It's been around 30 years. So if you want to guarantee that we can recover after a fault occurs, traditionally, I think energy control centers are doing about 200 simulations every day. In the future, we're probably going to have to do 2,000 simulations every day. And the reason why we're going to have to use 2,000 simulations is traditionally, when we turned the generator on, the generator ran all day. We backed the load down at night. We increased the load in the daytime, but the generator was always on the system. When I'm looking at renewable energy sources, solar is going to be off at night. Wind is going to be on and off on the days, depending upon weather conditions. So anyhow, that's why we're saying you have to run a whole bunch of more simulations, and they have to be automated. They have to be outage linked, and you're going to have to do them for every hour of every day. So I'm looking about this and getting the transitional models. If you look at the models that I've got in today's load flow, I've got resistance heaters and I've got induction motors. When I look at enhanced models, we're going to still have resistance heaters, but we want to put in fan and pump motors, and the model is going to be a function of voltage, speed, and torque of the motor. And we're going to put in air conditioners separate from fans and pumps. And once again, the model's going to have the model's going to be a function of motor voltage, motor speed, and motor torque. We're going to have to put in EV, electric vehicle chargers separately, and distributed energy resources separately. So the model is going to get a lot bigger. In the enhanced models, resistance loads are still going to be resistance loads. The fan, pump, and air conditioner models are going to change with voltage. We're thinking that there's going to be two models, one at 100% voltage and one we would use at 70% voltage. The air conditioners are going to be modeled differently than the fans and the pumps. The battery chargers, they're going to be modeled as constant power loads. And distributed energy sources, they have to be modeled based on the ambient conditions. And you got to remember that they're sensitive variable energy sources. So looking at this, our applications of the models, we're going to create a 100% model and a 70% model for each neighborhood substation. We're going to use a short circuit program to develop voltage profiles. The graph that we showed earlier that had bus A, bus B, and bus C on it, I have to find out which of those lines the voltage is at each substation. So what I'm doing is I have to place a fault at numerous places around the system and find out how a fault at that location affects the loads that are attached to neighborhood substations or supplied by neighborhood substations. So I'd use the 100% load model at any neighborhood sub where the voltage is greater than 80%. And I'd use the 70% load model at neighborhood subs where the voltage is less than 80%. And so what I have to do is right now I'd have to manually change my model from one condition to the other. And I do all my load flow studies assuming the transformer taps are fixed at their normal position. And if the voltage is less than 80%, and I'm going to have to consider putting in power factor biased under voltage relaying. Right now, I protect against grid collapse by putting in under frequency relaying. Under frequency relaying operates when the amount of generation is less than the amount of load on the power grid. I think that you need under voltage tripping as well as under frequency tripping, but we think you have to bias the under voltage tripping by the power factor of the load on the system. If the power factor is unity, I don't have motors accelerating and I get a marginal improvement when I shed load. If I've got motors accelerating, that would indicate the power factor poor. So say if the power factor is 70% after 10 seconds, that says motors are still accelerating after 10 seconds. And what I would do is I would shed load at that substation. And I'm shedding load to try to prevent a wide area grid collapse. So if I'm looking at the power factor biased under voltage relay settings, everybody's familiar with the time dials that you have for overcurrent relays. And the time dials on overcurrent relays are, they have multiples of, or amperes of pickup. And so this is a voltage. So what I've got on the horizontal axis is the percent voltage. And what I've got on the vertical axis is the time in seconds. And this is showing two time dials. The first time dial operates in 3 seconds. The other time dial operates in 6 seconds. And as the power factor improves, the delay that I'm willing to give the relay increases. So if I'm looking at time dial 1 here, if the power factor is 70% lagging and voltage is 95% for 6 seconds, I'm willing to shed load. If the power factors at Unity, I'm not going to shed load until about, this looks like 9 seconds. So this curve has the same point at 40%, but the time changes or expands as the power factor changes as a function of voltage. So I'm thinking about this and other future models. What other future models do we have to come up with? Well, we think you need frequency excursion models. I've spent a lot of time looking at blackouts, and I'm thinking that the models that we do for load flow should be duplicated for models we do for frequency excursions. And we should be routinely calculating system frequency as well as system voltage. And this leads into using electric vehicle battery chargers to respond to frequency deviations. In the near future, let's say 2040, that's not that far away, right? We're thinking there's going to be millions of EVs out there that are connected to the system at various times. So if the frequency is between 59.98 hertz and 60.02 hertz, all my electric vehicles would operate in a normal mode. If the frequency goes high, and to me, high is 60.02 hertz, any electric vehicle battery chargers that I have connected to the system, if they were just in a standby mode, I want them to transfer to the over frequency mode and immediately start consuming energy, and that'll bring the frequency down. If the frequency is between 59.92 hertz and 59.98 hertz, I would have all my electric vehicle battery chargers transition to a standby mode. If the frequency drops below 59.92 hertz, the electrical vehicles would transition to the under frequency mode. This is what we're doing in Australia on the Hornsdale Power Reserve right now. They're not using battery chargers for, I should say, they're not using electric vehicle battery chargers. They've actually got a large battery installed there. And if they lose generation, the battery will work for 10 minutes until they could bring up some quick start generation and recover the grid. And what that does is it reduces the spinning reserve costs on the power grid.